Hi, so today we're going to be solving Poisson's equation. And well, before we get on to actually solving the problem, we're going to see some properties about Fourier transforms because we're going to be solving it using this wonderful tool, the Fourier Transform. So, well, Poisson's equation is this one I have written here, but before we get on to that, let's just do a quick recap about Fourier transforms, okay? So, well, all these properties are the ones that we're going to be needing in order to solve this problem. And well, they are written in for a case of one variable, right? For a case of f of x or g of x, a function depending on one real variable, x. But they can be extended to a function depending on n variables by using this notation. We will just substitute x by a vector r, which is just composed of x1, x2, x3, so on, the coordinates of that vector. And well, let's just get on with it. So, in order for a function g of x to belong to this set of functions, okay, this is called the L1 space of functions, or also called the absolute integrable functions. Well, the only property it has to hold, really, all the functions belonging to this space satisfy this property, right? So if g of x belongs to L1, just a quick note. This L is the beginning letter of Lebesgue, of the Lebesgue name, right? So this L is in honor to Lebesgue. So, well, that's just a quick note. If this function belongs to the Lebesgue 1 space, this implies that this integral, right, the integral of its absolute value is less than positive infinity. That is, it is finite. And well, from minus infinity to positive infinity, because here we have r, we are integrating on all the real numbers. Okay, so if we have a function belonging to that space, then its Fourier transform exists, and not only that, but this Fourier transform is always bounded, it's always finite, less than infinity. Another important property is that, well, if I have a function g of x and g prime of x, which are continuous on R, really the property is that they are quasi-continuous. And quasi-continuous is just like continuity, but with a finite number of discontinuities. But if they are continuous, they're also quasi-continuous. So it doesn't matter, it's just a technical detail. We're going to assume that g of x and g prime of x are continuous on R. This implies that, of course, if they have their Fourier transform, right, the inverse Fourier transform exists. Okay, so they have to be continuous. And of course, g of x has got to have a Fourier transform, which is given by capital G of k. Now, before going into this property, we're going to talk about this one. And well, if we have f of x and f prime of x and f double prime and so on up to the nth derivative of x, and all of these functions are continuous on R, and also they have a Fourier transform, then what we get is that the Fourier transform of the nth derivative is given by ik raised to the nth power times the Fourier transform of f, which is denoted by capital F of k. Okay, this property can be proven, and all of this, where I will go into more detail in other videos, but for now, let's just do a quick recap. Okay, well, now, in the case of multivariable functions, right, for example, if f is, instead of being f of x, is f of a vector, this is just notation, this is not really a vector, this is just the same as x1, x2, so on up to xn. So in that case, the Fourier transform of the Laplacian, remember that the Laplacian is the divergence of the gradient of a function, it's a scalar, then the Laplacian is equal to minus this vector squared times the Fourier transform of f. And what is this notation? What is a vector squared? Well, the notation we're going to be using is that, well, k squared is really nothing but just the dot product between k and itself. And, well, this can be expressed as the modulus of k times the modulus of k again times the cosine of the angle between them. But the angle between two vectors which are exactly the same is just 0. Well, you say 0 degrees, so this is just the modulus squared, which can be expressed as just this k. So whenever we write this vector squared or this modulus or this k squared, we're just actually just referring to the modulus of the vector k squared, of course. So that's another property. And last but not least, the convolution theorem. First of all, what is a convolution? Well, a convolution is another operation that we define as follows. If we have a function g of x, another function h of x, the convolution denoted by this star, right? This star here, is just the integral from minus infinity to positive infinity of the first function, right? The first function was evaluated at g of x, but inside the integral, it's evaluated at g of x minus s, where s is just some other variable with, it's not, you can choose any name, right? It's just a different variable than x. What this actually does is just that it shifts the function. For example, if it was centered at 0, it is now centered at s, at x equals s, right? Because here, g of 0, well, this transforms into g of x has got to be s for it to be 0, so this will be g of 0, and this with the same value. Okay, so well, it's just shift up to x equals s. Now, yes, so we have this function, we just shifted times the original function, but evaluated again instead of x on x, evaluated at s. So this is the integral we get, and notice that it is integrated, right? The differential is with respect to s, so we're integrating with respect to s. Finally, we would get a function on x. And well, as I said, to generalize all these properties up to functions depending on n variables, just replace x by r vector and s by s vector. It's not 100% rigorous, okay? You cannot just do this, but the results still hold. If you want proofs or more details on it, we will do it, but not in this video. In this video, we're just going to be solving this equation. So before we get into the problem, let's just remind ourselves what the Fourier transform is defined as. So the Fourier transform of a function on x, okay, we take the Fourier transform of this function and it becomes a function on k. This is what this parenthesis means, that this Fourier transform becomes a function on k. And we're using k for the new variable. And well, we're going to define it as the integral from minus infinity to positive infinity of f of x times this phase. Of course, integrated with respect to x, so we get a function on k. Now, of course, we are not going to be using this exact definition because we are in the multivariable case, so we are going to be taking the Fourier transform of a function which depends on r. And in our case, r is going to be x, y, z, because we're going to be working in the three-dimensional space, three-dimensional real space. So the Fourier transform is going to be the integral from minus infinity to positive infinity, the integral from minus infinity to positive infinity, and again the integral from minus infinity to positive infinity, okay, over all the real space of my vector function, well, not vector, scalar multivariable function of e to the minus I k dot product, in this case, r, dx, dy, dz. And this can be written in a more concise manner as the volume integral, over R3, all the three-dimensional real space of my function again, of e to the I k r dv. This notation is actually more useful because here we are assuming Cartesian coordinates, but here, just depending on how we define the limits and how we define dv, we can actually work in polar, spherical, or really any other kind of coordinates. So, what does this mean? Well, it's just that product, right? If we define k as k1 on the I direction is the direction going on x, j is the direction going on the y axis, and k is it, well, not just k, I'm going to call it ec, sorry, not the I, but ex and ey. Okay, so these are the three unit coordinate vectors. So instead of I, just gonna write EX so we don't get mistaken. Okay, 2 EY and EC. And likewise, R is just this. Y on the Y direction and Z on the Z direction. And the product is just really multiplying the components. So the product would just be K dot R is just K1 X plus K2 Y plus K3 is Z. Now, of course, this can also be written as the modulus of K times the modulus of R times the cosine of the angle between them. And this is how I'm going to denote the angle between them. Okay. We're not going to get into that now, but afterwards we'll see how we can make a good choice of axes such that this angle is real nice to work with. And of course, if we define the Fourier transform, we can also define the inverse Fourier transform, of course assuming that this new function, which I'm going to call capital F of K vector, is it has an inverse Fourier transform. So the inverse Fourier transform, we're going to be defining it again as a volume integral. In this case, over R32, really it's just the real space again. Well, f of k vector e to the plus ik dot r, but in this case, this volume is going to be with respect to k. So we're no longer going to be working in these coordinates, but actually on the k coordinates. So I'm going to write this new volume as d vector k3. And this doesn't mean that it is a vector differential. It just means that, this is just the notation for dk1, dk2, and dk3 in Cartesian coordinates, or really just the volume differential, but as seen on the k coordinate axis. We're going to get into that afterwards. Now it's just a quick heads up. But of course, we need a normalization. We always need a normalization with the Fourier transform. And the one we're going to be choosing is 1 over 2 pi cubed. Notice that it is the same as the usual normalization for one-dimensional inverse Fourier transform, but cubed, because we have three integrals. It's like we're multiplying three Fourier transforms. And well, with all of this out of the way, we can actually start looking at the problem. So again, as I said, it's just a real quick reminder on Fourier transforms and the properties we're going to be using. If you want more details, just look into my channel. I will be making videos in more depth with proofs and everything on all of this. Now, this problem right here is, well, let's just explain what it is. So we are on R3, right? This space is R3, a regular 3D space. And we're going to choose a coordinate axis with origin at O and, well, the axis X, Y, and Z, which are perpendicular to each other, with the directions EX, EY, and EC. And now we have an arbitrary volume here, denoted by V, with some arbitrary charge inside. And rho is the charge density per unit volume. So, yes, so that's what we are going to be working with. So we have this arbitrary distribution of charge, and of course it's going to generate some electric field, and that electric field is going to have associated with it an electric potential, which will be denoted by phi of r. Okay, so what we want to do is to find the potential phi everywhere in space, and to do it, we can use the general Poisson's equation. Poisson's equation just tells us that the Laplacian of the electric potential is equal to minus the charge density we have in space over epsilon naught, which is the permittivity, the electric permittivity on vacuum. Before we get onto the problem, let's just see where this actually comes from. If we look at Maxwell's equations, in vacuum, we're assuming that there's no materials here, just vacuum, pure vacuum. Maxwell's equation describes the behavior of the electric and magnetic field and actually gives us all the information we need. So, in vacuum, Maxwell's equations are, well, the divergence of E, which is the electric field, is just the charge density per unit volume over epsilon naught. The divergence of B is always 0. The curl of E is, well, it's just minus the time derivative or partial time derivative of B with respect to T, well, just time derivative, and the curl of B is just mu naught, which is the vacuum permeability, times the current density, which I'm going to be denoting by J vector K, sorry, C of current, mu naught times this generalized current, which is called the displacement current. Okay, sorry, this is the conduction current, that's why I wrote a C, and this other current is the displacement current, and it's given by epsilon naught times the time derivative of E, or G, of E. And well, just real quick, this just tells us that the electric field has scalar sources, which are given by charges or charge densities, that the magnetic field has no scalar sources, that is, that there's no magnetic monopoles, at least that we know of. If there were some, if some were discovered, this term will have to change a little bit, and this term will have to change a little bit to include some kind of magnetic current. This is the curl of E, which is equal to minus the time derivative of B, and this really is just the Faraday-Lenz law. This is Gauss's law for the electric field. This can be called Gauss's law for the magnetic field, and this is the Ampere-Maxwell law. It just tells us that, well, here, just going back, this just tells us that a boring magnetic field can create an electric field, and here, well, a moving charge, which is represented by a current, right? A moving charge, plus or minus, moving, it just generates a current. Oh, it is actually just a current. So this also generates a magnetic field, and also a time-varying electric field creates a magnetic field too. In our case, there we have this term because there is some charge density. Nevertheless, we are assuming that there is no magnetic field, so we are assuming that V is actually equal to 0. So this really doesn't tell us anything. This is, we can just get this out of the picture. We don't need it. Here, well, this could just be 0, really, because the time derivative of 0 is just 0, and here we are assuming that we have no conducting currents, so this would be 0. Does the electric field change with time? We're going to be assuming that it does not, because of course if this is 0, this just implies that the curl of B is 0, and well, this implies that the time derivative of E has got to be 0, of course, assuming there's no conducting current. Is 0, this just means that E does not depend on T, so E really is just a function on the position on R, because there's nothing varying on time. Okay, with this in mind, really all we need is this equation. But to put it in a more useful way, we know from electromagnetism theory that we can define vector potential and scalar potential. So from the equation that I just erased, from this, well, this implies really that B can be written as the curl of some vector A. Why? Because if we replace this here, the divergence of any curl, I will prove this in other videos, is just 0. So there is some vector A that satisfies that this curl is equal to B. And this is called the magnetic vector potential. We are assuming that in this case, there's no magnetic vector potential and no magnetic field, so this will just be zero. But let's just keep this in mind. And also we can define, yes, from this equation here, from the Faraday-Lenz law, we can say, well, why don't we just define E as this? Might seem a bit arbitrary, but just hear me out for a minute. We're going to be defining E as the sum of a scalar potential, electric scalar potential, and the magnetic potential, taking the derivative with respect to time. Why? Because if we plug this in here, the equality still holds, because the curl of this expression, let me just, okay, so the curl of this expression is actually just this. Why? Because the curl of any gradient is zero always, and the curl of this, assuming that we can take the partial derivative out of here, we can interchange the limits, we get that this is just the minus the derivative of the curl of A. And as we said, the curl of A is just B. So this would be minus the derivative of B. Okay, so we have the same quality. So we can actually just define B in terms of this vector potential and E in terms of a scalar and vector potential. In this case, we do not really need the vector potential because there's no magnetic field, so we can choose A equals 0. This will give us that B is equals 0 and that this goes away. So we are really just working with an electrostatic case in which E is just a function on R, it does not vary with time, and also it can be expressed as the gradient, or the minus gradient in this case, of some scalar function phi, which is the electric potential. And now substituting this expression here, what we get, let me just erase this real quick. What we get is the divergence of, well, E is just given by this expression, so the divergence of minus the gradient of my electric potential is just the charge density over vacuum permittivity. Well, of course, the minus sign can go out of the derivatives or the gradient, out of the divergence, because of course it's a constant. And we can rewrite this as the divergence of the gradient of some scalar function, which is the, as I said, the potential. It's equal to minus the charge density over epsilon naught. And as I said before, the Laplacian is just defined as, well, let me just put defined here by the gradient, the divergence of the gradient. So this can just be written as, I'm sorry, it's getting real messy here. I'll try to make it more organized. It's just, the Laplacian of this scalar function phi of r. Well, this is just equal to minus, as I said, this vacuum permittivity and charge density. And of course, this is the equation we have. This is called Poisson's equation. Poisson's equation. Now just imagine, just real quick, that there was actually no charge here, that rho is equal to 0. Then what we get is that the Laplacian of our potential is just 0, right? It seems easier, it's an easier equation. And this is what's known as Laplace's equation. And well, just real quick, again, I'll just tell you what the Laplacian means explicitly. And the Laplacian, or how it's defined, is just the double derivative with respect to x plus the double derivative with respect to y plus the double derivative with respect to c. Of course, this is expression in, sorry, this is just the expression on Cartesian coordinates. In spherical, cylindrical, in general any kind of coordinates, this expression will change a bit because the derivatives will have different expressions. But in general, in Cartesian coordinates, sorry, this is the expression we get. So, well, now that we have made this recap about Laplace's equation, Poisson's equation, Maxwell's equations, and Fourier transforms, let's just get on with our problem. So, as I said, our problem is that we have some distribution of charge in space, defined by some volume, with this charge density per unit volume. And we want to find the potential everywhere. And to do it, we can use the general Poisson's equation, okay, derived from Maxwell's equations. And to do it, we need some boundary conditions. Usually when you have a partial differential equation, as is the case here, right, this just means that a partial derivatives, right, this is a partial derivative operator. Well, we need some boundary conditions to actually solve the problem. The boundary conditions we're going to be imposing are that rho and phi belong to L1. What this means is that rho and phi have a Fourier transform, both of them. So if that is true, then the Fourier transform of phi exists, and well, the Fourier transform of rho also exists. And another property or another boundary condition we want to impose is that phi x, phi y, phi xx, but all of these, right, phi x, sorry, phi y, or phi xy, and so on, are continuous and have a Fourier transform. Well, this notation just means taking for example, phi x is just a partial derivative of phi with respect to x, and phi xy is just a partial derivative of phi with respect to x, and then with respect to y, and well, so on, so on. So what this condition here is telling us is that we can use this property in 3 dimensions. That is, this holds, okay? Those phi satisfies that condition, then we can actually use this property here. And well, why are they actually boundary conditions, right? They're just like, okay, we are saying that these functions have some kind of properties. Well, the boundary conditions are really just because, for example, for this to hold, really, phi and rho have to decay when we go to the infinite fast enough such that there exists a Fourier transform. And likewise here, the derivatives have to go to 0 fast enough on the boundary, right, on the infinite, such that they have Fourier transform. But, well, okay. So all of that is just, I think, yeah, that's everything. That's all we need to actually solve this problem. So now we are ready to start solving this problem. Now, how are we going to do it? Well, this equation doesn't tell us anything like that, right? Why we cannot find phi real easily. How do we isolate phi? So to do it, we're going to take the Fourier transform on both members. So taking the Fourier transform in the first member, the Laplacian of phi, well, this is equal to the Fourier transform of minus rho over epsilon naught. And using this property here, using k as our new variable, we have, okay, this is just minus k squared, right, remember, the modulus squared of k, times phi of k, where we are going to define phi of k as the Fourier transform of my potential. Okay. Likewise, well, here minus 1 over epsilon naught is a constant, so we can come out of the Fourier transform, which is really just an integral, and we get minus 1 over epsilon naught times the Fourier transform of rho, which I'm going to call capital P of k. So again, we have this notation. Sorry, the Fourier transform of my rho r, which is a function on k vector, as I said. So we have gone by taking the Fourier transforms. By taking the Fourier transform, we have gone to this equation. Are there any derivatives here? Just no derivatives. We can actually isolate phi. So assuming that k is not 0, okay, this implies, well, it's not 0. This implies that the modulus is not 0, because the only vector that has modulus 0 is the actual 0 vector. So with this in mind, we can divide by this, which is just the modulus squared, and we get that on this k world, right, on this transform world, this Fourier transform is nothing but k squared over epsilon naught times this. We have solved the problem in this new world, in this k world, but of course we don't want this capital phi. We actually just want the little phi. So that's what we have to do. So just notice how powerful the Fourier transform is. We have gone from a second order partial differential equation, right, a Poisson's equation, and by taking the Fourier transform, we have solved the problem, of course in this new world, but we have solved the problem without any major issues. So this is the power of Fourier transforms. Of course, the problem right now will be going back to our regular x, y, z world, but we're going to see that in this case it's not too hard to do it. So here we have taken the Fourier transform and gotten this expression. It's just this function 1 over epsilon naught k squared times the Fourier transform of the charge density. Yes, okay. How do we proceed from here? Well, now we're going to have into account the convolution theorem. Okay, so just notice, if we have a function g of x and h of x, we have Fourier transforms, and we denote them by g and h of k, then m of x can be defined as the convolution between these two original functions. Then the Fourier transform of it just becomes the product of these two functions. Let me explain real quick. So if I have g of x and h of x, and they have Fourier transforms, right? Let me just say I take the Fourier transform of both of them. Then the convolution between them, which I'm going to call m of x, right, is the convolution. Then by taking the Fourier transform of both members, we get that the Fourier transform of m of x is just the product of these two Fourier transforms. So the product of k times h. And we're going to define this as capital M of k. So this is what we get. Okay? Of course, g and h need to have Fourier transform, and m also needs to have a Fourier transform. So how does this really help us? Well, just notice that if we call, what do we call it? Let's just call it h. If we call h of k, this function right here, this becomes, let me just rewrite this real quick. This becomes a function on k, which is equal to a function on k again times another function on k. This is the exact same expression as this. We have a function on k which is equal to another function on k times another function on k. By taking the inverse Fourier transform here, we can get m of x. So here, by this convolution theorem, as we said, m of x, taking the inverse Fourier transform on both sides, this is the inverse Fourier transform of j of k, h of k. Okay? And, well, what is this? As we said, m of x is just the convolution between g of x and h of x. Okay? So here, our capital M of k is 5. So capital M of k just comes from the convolution of two functions. So really, we can say that phi of r is just a convolution of the inverse Fourier transform of this, okay, which would be little h of k, convolution, the inverse Fourier transform of this, which is just rho. This is our expression for phi. But what is h of, sorry, this is an r. What is h of r? H of r is just the inverse Fourier transform of h of k. Okay, if this is not too clear for you, let me just do it the other way around. If we say that phi has this particular form, by applying the convolution theorem, of course we know that phi has a Fourier transform, phi is just m here, h has a Fourier transform, which is g, g is h here, and rho has a Fourier transform too. So by taking the Fourier transform on m, which in this case is phi, we get capital phi, okay, Fourier transform of this, which is equal to the product of two Fourier transforms, these two. Okay, if this is too confusing for you, because it's the first time seeing it, you might want to take a look by yourself, just calmly, and see how this actually works. But of course I will be making more videos explaining all of this into more depth. But for now, just have into account that expressing phi in these terms gives us the correct answer, because we're taking the Fourier transform, we just get the previous result. So we know rho, and we are assuming that the problem gives us the value of rho, but we do not know h. So all we need to do to find our potential is to find h, just an inverse Fourier transform. And we're going to do it right now. So let me just erase all of this, and we write that there so we have more space. So after all of this, we get that my phi, my potential on the R world, the regular three-dimensional world, is the convolution of some function h times my rho. This will get. So all we have to do is to find h, as I already said. How do we find h? Well, let's just work it out. H of r is the inverse Fourier transform of this function capital H of k. And it's a function on r. Well, let's just write this. This is just the inverse Fourier transform of what is h? H is just 1 over epsilon naught k squared, which is a function of r. And this, by the definition we said about the Fourier transform that we want to be using, is just this following integral: 1 over 2 pi cubed, because we're in 3 dimensions, times 1 over epsilon naught, and the integral over R3, which is all the 3D space, of my function. Okay, this is just 1 over k squared because we have taken out the vacuum permittivity. So let me just write in another color so you can see clearly. this is our input. I don't know if you can see too well the color. Well, 1 over k squared times e to the minus, plus, in this case because it's the inverse, k r dk3. Again, this k3 is not that it's a vector, it's just that it is the volume differential as seen on the k-axis. And well, to work this out, we need to define a new set of coordinate axes. So let me just explain for a minute. Originally, originally we have this. Just draw it. Yes. So originally, we had our 3D space, and we defined this set of coordinate axes x, y, and z with its origin O. And now, our vector r is just described by, well, r is just x on the x direction plus y on the y direction and z, on the z direction. But we have another vector, which is k. What is k really? K is just another arbitrary vector, okay? It's just another vector. Let's just say that from this set of axes, we see that, okay, k goes, I don't know, something weird like this. It goes in this direction. So that's what we get. Now, how can we, first all of this is seen from this original set of axes. If we now define a new set of axes, okay, what we get is that k can be expressed like this, but in this new set of axes. Let me just explain for 1 second. So let's just define a new set of axes like this. Let's say that, okay, with the same origin, but let's just say that this is k1, k2, and k3. Right? Okay, the coordinates of r will change, of course, and the coordinates of k will change. And now k will be given by k1 on this ek1 direction plus k2 on this k2 direction plus k3 on this ek3 direction. But of course, how can we choose this set of axes such that everything is real easy? We can choose this set of axes such that k3 is aligned with r. That is, we can instead choose this set of axes in which, okay, this k3 goes in this direction, and then just k1 goes in this direction, and this k2 in this direction. Of course, we're assuming they're perpendicular to each other. So with this set of axes, r is actually just r e k3. And why r? Well, because if we draw this new set of axes, let me just draw it for 1 second. K1, K2, and K3. Well, we said that we're going to choose them such that r goes in the K3 direction. So, well, how is r described? Well, there's no component on the K1 and no component on the K2 direction. And the component on the K3 direction is just the length of r. So it is just r, but in which direction? In the K3 direction. Let me just write this a bit better. On the K3 direction. And now K is just, well, it has some arbitrary direction. Let's just say that it goes in this direction. K. And it's described by, okay, its components in that direction. Okay? So now, to the matter at hand. First of all, what is this dot product? Well, let me just erase all of this. So 1 second. This dot product, as I said at the beginning of the video, it can be written as the modulus of k times the modulus of r times the cosine between k, of the angle between k and r. And this angle is really just the smallest angle between them, which is given by this. And we're going to call it theta. Okay, notice that theta starts at k3 and it spreads out until it goes to k. So it goes in this direction. I'm going to select that. And why is that a good choice? Because in spherical coordinates, if you know what spherical coordinates are, or you have some doubts about it, again, in my channel there will be videos explaining different kinds of coordinates in real depth. Okay, so for now, just trust me. This angle is the same as the angle we choose on spherical coordinates. So we can just write this as kr cosine of theta. So let me just erase this and write this expression we have seen. Yes, kr cosine of theta dk3. Now, how do we calculate this integral? A really nice approach is to go to spherical coordinates. Of course, spherical coordinates on this new set of axes. And what are spherical coordinates in this axis? Well, they're the same as in a regular axis, but changing x by k1, y by k2, and z by k3. So, in this axis, k1 is just the modulus of k, of the vector, times the sine of theta, where theta is this angle, as I said, and the cosine of phi. This lowercase, so this different phi, right? In LaTeX it's called bar phi, but I don't really know the name of this letter exactly. So this would be our bar phi. That's how we're going to call it. So on K2, it's just the sine again, but this time times the sine of bar phi, and K3, the cosine of theta. And our differential volume, dk3, which can be written as the volume on the k-axis, is just k squared times the sine of theta. And well, in spherical coordinates, instead of k1, k2, and k3, we actually have k, the modulus of the vector, theta, this angle, and phi, this other angle. So we have the k, d theta, and the phi. So replacing this right here, we get k squared, k squared, my sine of theta, dk, d theta, d phi. I'm running out of space, so just bear with me for a minute. Yes. And now, the only thing we have left are the limits of integration. And I'm going to erase this just for 1 minute. And well, okay. The whole of the three-dimensional space can be thought of as an infinitely large sphere. So, if we have our axis, K1, K2, and K3, just imagine an incredibly large sphere with radius going from 0 to infinity. So this is radius, let's just say that is k. So k is going from 0 to positive infinity. Why? Because the radius goes from 0 to infinity, because we have an infinitely large sphere. Phi, in spherical coordinates, goes from 0 to pi. Okay, it goes from 0 and it goes all the way up to pi radians. Okay, so this is theta. Yes, write this. Okay. And phi just does a full revolution around the k3 axis. So phi, which goes in this direction, just goes all the way like this. So phi goes from 0 to 2 pi. So this would be our description of R3 space, or the R3 space on spherical coordinates. So let me just write this. First of all, k, as I said, varies from 0 to positive infinity. Theta goes from 0 to pi, and phi goes from 0 to 2 pi. And now we have our volume integral converted into an actual integral which we can calculate. So there is everything expressed explicitly. So just yes. K squared and k squared cancel out. Remember, k squared is not 0, so everything works out fine. So we have 1 over 2 pi cubed, 1 over epsilon naught, and this integral. You just notice that, okay, this cancels with this, but there is no term with phi, with an explicit phi. So really, we can integrate from 0 to 2 pi. We can take everything out of the integral, and this integral is just 2 pi. So take this term, just is a contribution of the integral from 0 to 2 pi d phi. If you're not too sure about any of these things, just watch my channel. There will be some multivariable calculus courses and multivariable integrals and many things. Now, so we are left with the integral going from 0 to pi. Actually, the integral going from 0 to positive infinity, and the integral going from 0 to pi of the sine of theta e to the positive I k r cosine of theta d theta d k. Yes, dk. And you might be wondering, why have you changed? I understand how you have taken this out, but how have you changed these two integral signs? Well, the thing is that there's an infinite sign here, but that's not really an issue. We have changed them because the integration limits are not functions, they are constants. So because they don't depend on any of the variables, we can interchange them without any further complications. Of course, if the integration had some functions in it, changing the integration limits would be actually harder, and we have to do some more things. But in this case, that's not the case. Sorry, this is not the case, so we can just interchange them, of course interchanging the differential, and now we are integrating first with respect to theta and then with respect to k. Why? Because it's going to be easier. So let me just erase this. We keep on going up here. Well, 2 pi over this is just 2 pi squared, so we have 1 over 2 pi squared epsilon naught. The integral going from 0 to positive infinity, and here we are going to evaluate the other integral. Yes, theta is 0, and then theta is pi. What is this integral? Well, this integral is actually immediate. Why? Because here on the exponent, if we take the derivative with respect to theta, well, just square with me, taking the derivative with respect to theta of this exponent, we get ikr minus sine of theta. But here we just have sine of theta. But because ikr is constant in the theta world, we can just include it and divide by it. So what we're going to do is, okay, we have our sine of theta, but we are going to multiply by minus ikr and divide by minus ikr. So we have the derivative of the top function here. Just check for a minute. Yes. So the integral is just 1 over minus ikr, it's okay, e to the positive ikr cosine of theta. And if you don't trust me, just take the derivative and you get, okay, derivative of this is just minus IKR, this goes away, sine, and okay, we get the same as before. So this integral is actually correct. Let's just keep on going. And we are actually pretty close to the finishing line. There's a lot of chalk in here. So 1 over 4 pi squared. The 1 over minus I can go out. Actually, what is this? If we multiply by I on both sides, we get minus 1 and I minus, so this is just an I. Yes, that's just I. And the integral going from 0 to positive infinity of 1 over kr times, well, okay, of course this comes out because there's no theta, and if we evaluate this at pi, the cosine of pi is minus 1, so we get e to the minus ikr minus e to the plus ikr, because the cosine of 0 is just 1. And well, recall that the sine of alpha, some angle, is just e to the I alpha minus e to the minus I alpha over 2I. What we have here is this exact expression, but with the order inverted and without this 2I. So what we can do is say, okay, we need this 1 over 2I, so let's just include it. Of course, we have to multiply it so we don't mess things up. Okay, just this goes out, it's just 1. But here we have the reversed order, as I said. So let's just reverse the order. I include a negative sign here, and just include this negative sign here too. So what we get is that this is the sign, okay? This is the sign of, well, alpha in this case is just kr. The sign of kr. So, this is just 1 over 4 pi squared epsilon naught I times minus 2I, of course it comes out of integral, just I times I, psi squared is minus 1, this minus goes with this minus sign, and this is just 2, so this 2 goes up here, 2 over 4 is just 1. Sorry, 2 over 4 is just 1/2. Let me just, okay. Let me just write this a bit better because maybe it's not clear. 2 pi squared epsilon naught. And the integral going from 0 to positive infinity of. This has come out of the integral. We have kr dk, and all of this is just the sign of kr. Now, there could be a problem here if we have never seen this integral, but this integral is actually really famous. And, well, not exactly this integral, but really the integral, let me just write it here. This integral, which I'm going to call I, the sine of x over x, it's a really famous integral, and its value is pi over 2. Okay, this is really famous. And how do we actually get the value that this integral is just pi over 2? Well, we have to use complex analysis. Because the video, I think, is getting too long, I will not be doing it in this video, but I will put some links in the description or on the video, taking you to another video in which I calculate this integral, just a video for that integral, because it's really interesting. You'll see exactly why that's pi and pi over 2 and well. So, well, but we don't have that expression, we have this. We can just do the following change of variables. Here, just call q equals kr. The q is just r dk. So dk is just assuming r is not 0, of course, well, because it's dividing here. This is just, let me just write this. This is the integral from 0 to positive infinity. Again, if k is 0, q is 0, and if k goes to positive infinity, q goes to positive infinity because r is positive. Okay? Well, the sign of kr is just q over kr is just q again, just q, and dk is 1 over r dq. Because we're integrating with respect to q, r comes out of the integral. And we have that, well, let's just take it out now of the integral. And just put it right here, my r. And this is this integral. Of course, here's an x, here's a q, it's just a dummy variable, the relation is the same. So this, all this, is just pi over 2. And erasing this, I'm sorry I'm coughing so much because of a chalk. Yeah. What we get is 1 over 2 pi squared epsilon naught r times pi over 2, which really is just 1 over 4 pi epsilon naught r. And this is the sought for function. If you have seen problems or theory in electromagnetism, you might find this expression really, really familiar. But let's just see what the potential is actually. What's the expression? So I'm just writing here that h of r is 1 over 4 pi epsilon naught r. What we have, what we have is that the potential is nothing but phi of r. Well, it's just a convolution between h and rho. And what is a convolution? As I said, a convolution is just the integral from minus infinity to positive infinity. Minus infinity to positive infinity of the first function, in this case h, evaluated at, well, if it was in one variable, x goes to g of x minus s. In this case, we can call h of r goes to h of r minus, and this new function, we're going to denote it, this new vector, as r prime. Okay, this is not a derivative, this prime just means that it's another vector. So here we have r minus r prime times rho of r prime d r prime. Well, we know what h of r is, and just one detail here. Well, just write it here. H of r is 1 over 4 pi epsilon naught. It's just notation, but r is really just, this can be written as this, the modulus of the vector r. So, let me just make some space. By doing convolution, we get that h of r minus r prime is just 1 over 4 pi epsilon naught, the modulus of this new vector, r minus r prime. Yes. Okay, so that's what we get. Let me just check for a minute. Oh, yes. Really, it shouldn't be from negative infinity to positive infinity because we're in 3 dimensions. Really, this should be integral on R3. Okay? now it makes more sense. So we're just writing what h is. Just write this volume integral. Well, let's erase it. We get well, rho goes on top, rho on r prime, 4 pi epsilon naught r minus r prime d v dv or d r prime. Again, just like we did with the k vector, this is just the volume, but prime. What's the volume prime? It's just the same differential volume, but with the coordinates on r prime. Okay, so our coordinates will actually be dx prime, dy prime, and dc prime. It just means that we are integrating with respect to this other vector. Okay, it's just notation, as always. And now we can simplify this a little bit, having into account that this rho is of the following form, right? Rho is 0 outside the volume. Okay, then this volume, there's actually just charge density inside this volume, we said. Outside there's no charge density, so it is 0. And it has, well, its value, rho r inside V. So really, on R3, this is 0 outside V. So this is just the integral on V, because outside 0, of my rho, or evaluated on R prime, 4 pi epsilon naught R minus R prime dv prime. I'm going to say dv prime because we're integrating with respect to this new vector, or these new variables. So this is our answer, and I'm going to write it here a bit more nicely and do some comments, and we will be finished with our problem really. So our potential phi is just, well, this can come out of the integral 1 over 4 pi epsilon naught of the volume integral over v, and really this should be v prime because we're seeing it as this new vector r prime of rho r prime over the modulus of this vector. Okay, so yes, this could be our, let me just write this a bit, just to be. This could be our potential. And well, now, if you have taken some electromagnetism courses, you will notice that this is the actual expression you are taught. This expression for the potential comes from the Coulomb potential and Coulomb force. So this is a really, really well-known expression. And as you see from this approach, this term here actually comes from the convolution between two functions. This function and this other function right here, h. Well, really it should be h, lowercase h. And now r, this r is just the position of some point, right? This is some point on R3 where we want to calculate the potential, right? This is where the potential is being evaluated. And this other vector r prime is just a varying vector which goes to all of the points of our volume. So that's why we're integrating along this v prime. So r is a fixed point here, but r prime moves up to all the points in this volume. And here, on those points, we have to evaluate this integral. Well, yeah, that would be the problem. This is the solution. I think it's a really nice approach to this potential formula. And well, I hope you liked the video, and if you want more problems on electromagnetism or Fourier transforms and so on, you subscribe to the channel, and well, see you in the next video.